Good morning, students. In previous class, we studied about osmotic pressure. Today, our topic based on osmotic pressure or concentration of solution. The solutions are three types. Number one, A. Isotonic solutions. And number two, B. Hypertonic solutions. And number three, C. Hypotonic solutions. Let us discuss about the first one, isotonic solutions. The first one, isotonic solutions. Here iso means same. The definition for isotonic solutions: two or more solutions having same osmotic pressure or same concentration are called isotonic solutions. Let me take example. For example, in one beaker I am taking 0.01 m urea. 0.01 m urea. The urea concentration is 0.01 molarity. And in another beaker I am taking 0.01 m glucose. 0.01 m glucose. The glucose concentration is 0.01 molarity. So these two solutions having same concentration 0.01 m, 0.01 m. So these two solutions are called isotonic solutions because these two are having same concentration. Iso means same. Let me take one example for explanation. So this is the blood cell and this is the cell membrane, and it acts as a semi-permeable membrane. And inside the blood cell indicated by number 2 and outside that blood cell indicated by number 1. And that blue dots shows the water, means it is a solvent. And that red dots will shows the solute particles. And inside the blood cells, the NaCl percentage is 0.9%. Inside the blood cell, the NaCl percentage is 0.9. And we know that the saline will inject into our body. So inside the blood cell, the NaCl percentage is 0.9 m by v. In saline also, the NaCl percentage is 0.9 m by v. See here, this is saline. I round up the percentage of NaCl and it is 0.9% W by V. And we know that when the saline inject into our body, the saline will flow in blood vessels. And in that blood vessels, we have saline and blood cells. So here inside the blood cell, the NaCl percentage is 0.9 m by v, and outside the blood cell also, means in saline also the NaCl percentage is 0.9 m by v. So there are two solutions. Inside the blood cell one solution, and outside the blood cell also we have one solution. Inside the blood cell solution indicated by 2, outside the blood cell the solution indicated by 1. So these two solutions having same concentration. See here, the solute particles are same outside the blood cell and inside the blood cell. So these two solutions having same concentration. Consequently, these two are having same osmotic pressure. So these two solutions are called isotonic solutions. Outside the blood cell and inside the blood cell, the osmotic pressure same, means pi 1 is equal to pi 2 outside the blood cell and inside the blood cell, and the concentrations also same. C1 is equal to C2 outside the blood cell concentration is equal to inside the blood cell concentration. So here no net flow of H2O, no net flow of H2O, means here how many H2O molecules are enter into the blood cell, the same number of H2O molecules are leave from the blood cell or come out from the blood cell. So this is about isotonic solutions. Two or more solutions having same osmotic pressure or same concentration are called isotonic solutions. Due to isotonic solutions present in blood vessels, nothing will happen to blood cells. Next, second one, hypertonic solutions. Here hyper means high. Hyper means high. So the definition for hypertonic solutions: a solution having higher osmotic pressure or higher concentration than the other solution is called hypertonic solution. Let me take example. I am taking one beaker. In that beaker I am taking NaOH. The concentration 2m, 2m NaOH, 2 molar NaOH, and I am taking another beaker. In that beaker I am taking 0.5 molar. In this beaker I am taking 0.5 m urea. So these two solutions having different concentrations. The NaOH concentration 2m and urea concentration is 0.5 m. So this solution having high concentration than the second solution. So this solution is called hypertonic solution. When we compare these two, the first solution 2m NaOH solution is called hypertonic solution. A solution having higher osmotic pressure or higher concentration than the other solution is called hypertonic solution. Let me take one example for explanation. So here this is the blood cell and this is the out of the blood cell. The out of the blood cell indicated by 1 and inside the blood cell indicated by 2. And this is the cell membrane, and that cell membrane act as a semi-permeable membrane, and that blue dots shows the solvent, nothing but water. Here we are taking the water as a solvent, and that red dots shows the solute. So there are more number of solute particles outside the blood cell and there are less number of solute particles inside the blood cell, and this cell membrane act as a semi-permeable membrane. So here the osmosis will occur. The flow of solvent particles through a semi-permeable membrane from lower concentration area to higher concentration area is called osmosis. So here the solvent particles flow from lower concentration area to higher concentration area, means the water molecules flow from inside the blood cell to the outside blood cell, because there is a high concentration outside the blood and there is a less concentration inside the blood. Consequently, the water means the solvent particles flow from low concentration area to high concentration area. We know that inside the blood cell the NaCl percentage is 0.9 m by V. If we inject the saline which is contain NaCl percentage is more than 0.9%. So the saline contain NaCl. How much percentage? More than 0.9%. More than 0.9%. Means outside the blood cell there is a saline and that saline contain more than 0.9% of NaCl. So in that case the solvent particles flow from inside the blood cell to the outside blood cell. Consequently the blood cell will shrink. So this is the first position of cell membrane, and after inject the saline the cell membrane will come to here. So this is the second position of cell membrane after inject the saline, because the solvent means H2O molecules flow from inside the blood cell to the outside the blood cell, means the cell will shrink. The cell will shrink. And here pi 1 is greater than pi 2, means osmotic pressure outside the blood cell is more than the inside the blood cell, and concentration C1 is greater than C2, means the concentration of outside the blood cell is more than the inside the blood cell. So here net outflow of H2O, means the H2O molecules flow from inside the blood cell to outside the blood cell, and the shrinking of blood cells is known as plasmolysis. Plasmolysis. The shrinking of blood cell is known as plasmolysis. So here there are two types of solutions, outside the blood cell and inside the blood cell. Outside the blood cell having more concentration and inside the blood cell having less concentration. If you compare these two solutions, the first solution or outside the blood cell, the solution is called hypertonic solution. A solution having higher osmotic pressure or higher concentration than the other solution is called hypertonic solution. And next, third one, hypotonic solutions. Hypo means low. Hypo means low. A solution having low osmotic pressure or low concentration than the other solution is called hypotonic solution. Let me take one example. I'm taking one beaker. In that beaker, I'm taking urea, 0.05 m urea. The urea concentration is 0.05 molar. And I'm taking another beaker. In that beaker, I'm taking another solution, 2m sucrose. 2m sucrose. The sucrose concentration is 2 molar. When we compare these two solutions, the first solution is a hypertonic solution because its concentration is less than the second one. So a solution having low osmotic pressure or low concentration than the other solution is called hypertonic solution. So this is called hypertonic solution. And in this the second solution is a hypertonic solution because it having more concentration. So it is a hypertonic solution, and it is a hypotonic solution, it having less concentration. So a solution having low osmotic pressure or low concentration than the other solution is called hypotonic solution. So this solution is a hypotonic solution. Let me take one example for explanation. This is the blood cell in blood vessel. Outside the blood cell indicated by 1 and inside the blood cell indicated by 2. And the blue dots shows the solvent particles, means H2O, and the red dots shows the solute. And this one is the SPM, semi-permeable membrane. It is a cell membrane. That cell membrane is act as a semi-permeable membrane. Here outside the blood cell having less number of solute particles, and inside the blood cell having more number of solute particles. Outside the solution is a low concentration solution, and inside the solution is a high concentration solution. So according to osmosis, the solvent particles flow from lower concentration area to higher concentration area. So this is the higher concentration area, and this one is the lower concentration area. So here the water molecules flow from low concentration area to high concentration area. Means the water molecules enter into the blood cells. Then the blood cell will get swell, and swelling of blood cell is called hemolysis. Hemolysis. And we know that inside the blood cell the NaCl percentage is 0.9 m by. If in saline the NaCl percent is less than the 0.9, the NaCl percent less than the 0.9, then the solvent particles, means H2O particles, outside to inside the blood cell. Consequently the blood cell will get swell, and the swelling of blood cell is called hemolysis. So here two types of solutions, outside the blood cell and inside the blood cell, and these two are having different concentrations. So the outside the blood cell is called hypotonic solution because it having low concentration. A solution having low osmotic pressure or low concentration than the other solution is called hypotonic solution. So here pi 1 is less than pi 2. Pi 1 is less than pi 2. 1 indicate outside solution, 2 indicate inside solution. So that outside solution having less osmotic pressure than the inside solution, and outside solution having less concentration than the inside solution, C1 less than C2. And here net inflow of H2O. So this is about hypotonic solutions. In isotonic solutions, the solutions having same concentration, no net flow of H2O, pi 1 is equal to pi 2 and C1 is equal to C2. In hypertonic solutions, hyper means high, outside solution having more concentration than the inside solution, and outside solution having more osmotic pressure than the inside solution. So pi 1 greater than pi 2 and C1 greater than C2. And here net outflow of H2O, net outflow of H2O. And the last one, hypotonic solutions. Hypo means low, outside the solution having less concentration, inside high concentration, and outside solution having less osmotic pressure, and inside solution having high osmotic pressure. So pi 1 less than pi 2 and C1 less than C2. And here net inflow of H2O, net inflow of H2O. So these are solutions based on osmotic pressure or concentration of solution. Next one, abnormal molar masses. The colligative properties are depends on number of solute particles but not on their nature. We know that. The solutes are two types. Solutes are two types, electrolytes and non-electrolytes. Electrolytes example KCl, and non-electrolytes example glucose. And the colligative properties are four types. We know that. Number one, relative lowering vapor pressure, RLVP. P0 minus P by P0 is equal to N2 by N1 is equal to N2 means it is for solute, moles is equal to weight by molecular weight. So W2 by M2 into, and N1 it is for solvent. So M1 by W1. The second one, elevation of boiling point, delta TB is equal to KB into M is equal to KB. M means W2 into 1000 by M2 into W1. And third one, depression of freezing point, DFP, delta TF is equal to KF into M is equal to KF into M means W2 into 1000 by M2 into W1. And the fourth one, osmotic pressure, pi is equal to N2 RT by V is equal to N2 means moles weight by molecular weight of solute. So W2 by M2 into RT by V, RT by V. So these are the four colligative properties. In all these colligative properties, the colligative property is inversely proportional to the molar mass of solute. Means here M2 molar mass inversely proportional. In second one also inversely proportional. In third one also inversely proportional to colligative property. In fourth one also molar mass inversely proportional to colligative property. So we can write that in all colligative properties, we can write that colligative properties is inversely proportional to molar mass of solute. Relative lowering vapor pressure inversely proportional to molar mass of solute. Elevation of boiling point inversely proportional to molar mass of solute. And depression of freezing point inversely proportional to molar mass of solute. Osmotic pressure also inversely proportional to molar mass of solute. And simply we can write that colligative property inversely proportional to molar mass of solute. So here, when the solute is non-electrolyte, solute is non-electrolyte. There is no change in molar mass. No change in molar mass. And no change in colligative property. But when the solute is electrolyte, then the solute undergoes dissociation or association. Then the number of particles of solute increases or decreases. Then the colligative properties are abnormal. When the solute is electrolyte, the colligative properties are abnormal. There is a change in colligative properties. So we can write that definition. In the solution, the molar mass of solute either lower or higher than the expected value is called abnormal molar mass. So here, when the solute is electrolyte, then the solute undergoes dissociation or association. Then the number of particles of solute increases or decreases. Let me take dissociation and association. In dissociation, what happening? Let me explain. For example, 1 mole of KCl, 1 mole KCl dissolve in water. Then 1 mole of K plus ions and 1 mole of Cl minus ions are formed. So here we are adding only 1 mole of KCl in water, 1 mole. After adding, it dissociate into ions, 1 mole of K plus ions and 1 mole of Cl minus ions. K plus ions 1 mole, Cl minus ions 1 mole. Means we got 2 moles. In this case, the observed colligative property is higher. Observed means after dissociation. Then the calculated colligative property. Calculated means before dissociation. Before dissociation 1 mole and after dissociation 1 plus 1 2 moles. We are adding only 1 mole, but after dissociation we have 2 moles in the solution. So here let me take molar mass and here 2 moles. So here molar mass of solute is equal to expected value divided by 2 is equal to the expected value potassium and chloride. Molar mass is 74.5 divided by 2 is equal to 37.25 gram per mole. Here we are adding only 1 mole, so we have to take only 1 mole, but in the solution we have 2 moles. So here we have to take that expected value divided by 2, then we are getting the true 37.25 gram per. Means this value for 2 moles, but we have to take only 1 mole. So for 1 mole divided by 2 is equal to 37.25. So this is for 1 mole. So in the dissociation, the molar mass always lower than the true value So this is the true value, expected true value. And the number of affected particles increases in the solution. Here number of affected particles increases in the solution. So before dissociation we have only one particle. After dissociation we have two particles. So the number of affected particles increases in the solution. And now in association, for example, ethanoic acid dimerized in the benzene due to the hydrogen bond. Here 2 moles acetic acid forms only 1 mole of dimer. And here in this previous case 1 mole will form 2 moles. But in this association 2 moles will form 1 mole of dimer. Let me explain. So here 2 moles 2CH3 COOH, ethanoic acid or acetic acid, and this is the reversible process. And here we are taking 2 moles. That 2 moles will give only 1 mole of dimer, CH3 COOH, taken 2 times. So here only 1 mole, but here 2 moles. So 2 moles will form only 1 mole of dimer. So in this the dimer structure will be like this: CH3 C double bond O and OH, and another particle CH3 bond C double bond O OH. So there are two particles now, 1 plus 1, 2 particles, and the hydrogen bond formation takes place between these two particles. So here oxygen and hydrogen, highly electronegative atom and hydrogen bond formation takes place, and highly electronegative atom and hydrogen, between these two atoms hydrogen bond formation takes place. So two particles will give one dimer, means 2 moles will give 1 mole, and this is the hydrogen bond. So in this case the observed means after association. After association, colligative property is lesser than the calculated, means before association calculated colligative property. So the observed colligative property is lesser than the calculated colligative property. After association 1 mole, before association 2 moles. So here molar mass of solute is equal to, so here we are adding 2 moles, but in the solution that 2 become 1. So here also we have to take 2 moles. So in the calculation we have to take 2 into expected value is equal to 2 into, and acetic acid molar mass 60 is equal to 120 gram per mole. So in association the molar mass always higher than the true value, and the number of affected particles decreases in the solution. So before association 2 moles, after association 1 mole, means the number of affected particles decreases in the solution. So to overcome that abnormal values, the want-of introduced one factor, that is called want-of factor, represented by I. That want-of factor represented by I letter. So here I is equal to normal molar mass divided by abnormal molar mass. And I is equal to quanta factor I is equal to observed colligative property divided by calculated colligative property. And also we can write I is equal to quanta factor I is equal to total number of moles of particles after dissociation or after association divided by total number of moles of particles before dissociation or before association. And here for dissociation, the I value is greater than 1. I is greater than 1. And for association, and I is equal to unity for the solution, neither dissociation nor association. Neither dissociation nor association. I is equal to unity. I is equal to unity. I is equal to 1. Let me take examples. For example, I am taking KCl. The KCl dissociate into K plus Cl minus. Before dissociation 1 mole and after dissociation 2 moles. And here I is equal to total number of particles after dissociation divided by total number of particles before dissociation is equal to total number of particles after dissociation 2 1 2 divided by total number of particles before dissociation 1 is equal to 2. So here I is equal to 2, means for dissociation the I value is greater than 1. So here I is equal to 2. It is greater than 1. We take another example. Two CH3 COOH gives rise to CH3COOH taken 2 times. It is a dimer. And here 2 moles. And after association 1 mole, because there is 1. And here I is equal to total number of particles after association divided by total number of particles before association. is equal total number of particles after association 1 divided by total number of particles before association 2 particles. 2 1 by 2 is equal 0.5. So here I is equal to 0.5, means it is less than 1. So here for association the I value is less than 1. So here we got I is equal to 0.5. So the want of modify the colligative properties by taking the want of factor I. So here the colligative properties, number 1, relative lowering vapor pressure is equal to P naught minus P by P naught is equal to I factor, want of factor, N2 by N1. And the second one, elevation of boiling point delta TB is equal to I into KB into M. And third one, depression of freezing point delta TF is equal to I into KF into M. And the fourth one, osmotic pressure pi is equal to I into N2 RT by V. So these are the modified colligative properties. So this is about abnormal molar masses.